Okay, good morning, everybody. So the topic of my talk is self-organized criticality, and in particular, it's a variant of the Sandpile models. So one of the Sandpile models that's already very well known in the literature. And I'll be showing mostly numerical results, maybe not completely, but most of the numerical results have been done, and I will show them in next 35 minutes or so. So the idea of self-organized criticality was introduced by Bach, Tang, and Weisenfeld about more than 3 decades before, and they had a very ambitious proposition. They claimed that they know the answer of the question that why in nature long-range correlations are ubiquitously seen in different systems and phenomena. In particular, they had in mind the energy bursts in solar flares, their distributions, or the energy released in seismic events of earthquakes, or say river networks, the drainage distributions, or even in sandpiles. So they said that the way we are accustomed to see long-range correlations in laboratories, like paramagnetic to ferromagnetic transition, you tune a control temperature like control variable like temperature, arrive at the critical point where you see these long-range correlations, appearance of long-range correlations. And now in nature, there is nobody to tune that, to do that job, tune the control parameter. So how in nature long-range correlations are observed? Their answer is that these systems have self-organizing mechanisms. They evolve, their dynamics in such a way that they evolve in a state where they see the fluctuations of all length scales, which are treated as the signatures of long-range correlations. So that is their idea, and they expressed their idea in terms of a small toy model, and that is called Sandpile model. So we go to the next slide to explain how the Sandpile model works. So those who don't know, for them, at least to my students, I like to explain in this way that you consider a chessboard, actually much larger than the 8x8 chessboard, L by L chessboard actually. And at each square of the chessboard, you put blocks the way the children play, or blocks one after another, cubic blocks. And so if you do that, if you in computer, you just use a two-dimensional array and define a height variable associated with each site, each location of the two-dimensional array. You add a sand grain by increasing the height variable at that site by 1. Somewhere here, yes. And so you can say, so what is the big deal? This is the random deposition model. Actually not, because there is a stability condition associated that the height at a site become unstable if it reaches to a value z here, and or exceeds that number, then there is a the stability is lost for that sand column at that site, and then there is a toppling. In a toppling, the sand height that loses z number of grains, and each neighboring site gets 1 grain each. For a square lattice, this z is equal to 4, and so all the nearest neighbors get 1 grain each. So a stable height for Sandpile model on square lattice, the stable heights are 0, 1, 2, 3. So that is my way of definition of the stable sand heights. So other authors may do something else. Okay, so these four points, if we understand, then the understanding of the Sandpile model is complete. There is the outflow of sand takes place at the boundaries, because some boundary sites are have 3 or 2 neighbors within the system. So the rest of the particles, they go out of the system and they never come back. So that is the outflow current. Initially, the outflow current is almost 0, but the inflow current is constant. 1 by 1, you are dropping the sand grains. After dropping a sand grain, you wait for the activity to die down. Then you get another stable state. So a drop of a sand grain, it takes you from a stable state to another stable state. Is the transition is carried out by dropping a sand grain. So this is the inflow rate. The outflow rate gradually builds up, and then there is a situation when the inflow rate is equal to outflow rate, and that is called the steady state. One needs to understand there is a multiple toppling possible. In an avalanche, a site may topple more than once, and a typical very small example of this is this, that this is a stable state. You can understand all sites are either 0, 1, 2, or 3. And then you add a sand grain at the center site, then that will make the 4 neighboring sites unstable. And then these sites will topple, and they will donate 1 grain to the center site. This will topple again, and finally the stable state is this. So this is the initial stable state. You add a sand grain, it takes to the final stable state. Here, the number of steps you do, that is actually counted as the time. So this t equal to 0, 1, 2, 3, 4 is the time here. And it has been seen that this is happening in a domino process, and S, the total number of topplings in this is called an avalanche. Total number of topplings in this avalanche is the size of the avalanche, and the number of times it takes, number of sweeps it takes to die down, that is the time lifetime of the avalanche, and both the quantities are power law distributed. So these are the, so this finishes the description of the Sandpile model. And now we discuss this, that this is this dynamics is abelian, and Deepak invented this. Deepak put forward his in his 1987 paper. This is the observation that when a number of sites are active, in the sense they are unstable and they are going to topple, then it doesn't matter that which order I topple active sites. It and independent this the final stable configuration is independent of this order in which one is one activates this one takes the toppling events done, and this is in this. So in this is again a very small example where 2 particles are dropped in 2 different corners, 2 opposite corners, one here, and one there. And if they are done in the other way around, then we get the same same final state. So now I come to the modification that we will be interested in this work. This is the restricted height Sandpile model, and that has been introduced by Dickman et al. In 2001, I guess. So restricted height Sandpile model. Sorry. So this is nothing but adding one more constant to the system, ordinary BTW Sandpile model. And this constant is that the height has to be maximum, has a maximum value HC. So for a active site, the height can be at within this range greater than equal to Z and less than equal to HC. So in a toppling, an active site, that actually means in a toppling, whenever the site is toppling, it will pass 4 grains, 1 grain each to the neighbors. But every time before passing the grain to the one of the neighbors, it will check whether its height is less than HC or not. So that is the restriction. A very subtle restriction, but we will see that in some cases this will make a difference. The first difference is this is no more, the model is no more abelian. Why? Because this is, suppose consider the 2 sites which are active and they are trying to donate grain, 1 grain each to a third site. Ij are active and K is inactive. So one needs to check that if K, after getting grains, it is still less than HC, the height is less than HC or not. Suppose the height of K was HC minus 1. So out of I and J, whichever is giving a grain to K, that is, so he will win, that side will win. The next site will not be able to transfer a grain. So it depends on whether you update I first or J first or I, depending on that, the final configuration will be dependent. So that is why it's a non-abelian dynamic. And in non-abelian dynamics, then...
Excuse me, can I ask a question? So the number of sites that you, so when you have to do the toppling, let's say that you have 4 neighbors, so you can give 4 grains, but if one is bigger than HC, you give only 3 grains?
Absolutely right.
Yeah. Okay.
Yeah.
Thank you.
So, so you keep three grains there, and so it is like this. So how much different is the model? We ask the question, how much this model is different from the BTW model? So first check, begin at the beginning. So let us first check that whether it depends on how it depends on the initial condition. So, and compare, most of my slides are on the left BTW and on the right non-abelian BTW. So I compare. So here is the comparison that I start from 7 different initial conditions. So initially all scratch, total empty lattice, then average density half, average is 1, 1.5, 2, 2.5, and 3. And similarly here. So we see that here also it goes to a steady state with an average height, but compare the average height here. For this lattice size, this average height is 2.118 and it is 2.055. Our numerical result says that the final in the infinite limit it will be 2.057, and for BTW there is an exact result by Professor P.S.F. of Dubna University Group, and they said it is 2.125, 2 plus 1 by 8. So this is already a difference in the average height in the stationary state. There is another difference is there that I'd like to draw your attention to note. See here, this when it was 3. So when it was 3, that means the starting configuration, all sites are 3. So this is the maximal height, maximal number of grains you can put in the system. In that case, you just drop 1 sand grain, and then after that sand grain, 1 sand grain, and the average height came down to 2.984, and here the average height came down to 2.058. So this is, I didn't check it is already in the stationary state or not, but this is very near to the stationary state, this value, but here it is far from the stationary state and it actually goes down like this. Why this happens, that I will clarify later, that there is a limit, there is a upper limit to how many particles you can flush out in BTW model, and then in this model either there is no limit or the limit goes as L square. Here it is L. Okay, so I zoom this part, the stationary part here, and the zoom part looks like this. And so this is the average height, average value of the height. Here, 2 different values, and I now measure the width of this fluctuation, and this is sigma, And here I see that these two variations, this is 1 by L variation for BTW, but for non-abelian BTW, it is like this. And it seems it may go to a saturated value. And so I deducted this much amount from sigma, and then after that it is log scale, it becomes straight and like this. So it may happen that it will reach to a constant value, and that actually means that the fluctuation here, okay, I cannot see into 256 lattice size, but in larger lattice sizes like 512, these the difference is more. So fluctuations are much more in NABTW than this BTW case. So why, that will also be I will give you some information for that. So this is again Deepak's prescription of characterizing a steady state, and the characterization is done in terms of defining a forbidden subconfiguration and transient and recurrent states. So what is forbidden subconfiguration? That is interesting, and let us start with here. So for a forbidden subconfiguration in a BTW model, the simplest possible example is a 0, 0. So these two sites, neighboring sites, which are having heights 0 and 0, you can never find in the stationary state. Why? Because each one of them is having a non-zero probability to get a toppling. And if there is a toppling at this on the left side, so this will give a 1 grain to the right side, and similarly same for the right side also. So in the stationary state, you will never get a pair which are simultaneously 0, 0 in the stationary state. Exactly by similar logic, you cannot have a triplet like 0, 1, 0 in the stationary state. You cannot have a 0, 0, 0 also in the stationary state. In the stationary state, you can't have have 4 sites cluster whose heights are 0, 0, 0, and 2. That is also not possible, again because of the same reasons, that if these sites topple, then it will get 3 particles, but 2 particles are less than that, so that is also not possible. So by this time you can you have already started guessing that what is the general rule for defining a forbidden subconfiguration, and that is here. Oh, sorry. Okay, okay, I'll come to that. So before that, let me see that the BTW and NABTW, so they lead to defined stable configuration. So let us start with this configuration in both cases, and I add a sandgrain here. So there is a 4, and then it flushes out 2 particles outside the boundary, and 2 particles within this. So this is 4, 4, and like this. In BTW, these 2 4 sides, they topple simultaneously, makes it 5, and then this is the stable configuration. But this does not happen in any BTW. Why? Because these 2 4 sides, they are now their order is important. Suppose I topple this one first, so that will actually donate one sandgrain here, make it unstable. And when this site is toppled, it cannot donate a grain there. That's why it remains 1 there. And so final configuration is this, which is defined from this. Okay. So this actually means, this example means that the transition from this state to this state and from this state to this state, they are different. So this configuration, this stable state is more probable compared to this state. So this because of this type of transition, this this configuration is getting a less probability, and this configuration is getting a more probability. And this we'll see that these are non-uniform. The BTW recurrent states, probabilities of the BTW recurrent states are non-uniform. So we consider a 2 by 2 lattice, and then we make this number. We define each configuration of the 2 by 2 lattice configuration, stable states, by this number k, and we count that number. There is counting how many forbidden subconfigurations are there. Their number is 64, number of recurrent states 92, for 2 by 2 square lattice, it's easy. You have to make a doublet in 4 possible ways, in triplet in 4 possible ways, and in 4 sides in 1 possible way. So you get 64 here. And this is just numerical measurements. I dropped 10 to the power 8 particles and then counted each configuration. And from this, I defined a value of K, and this is the probability distribution. All are uniform within experimental level. But in NABTW, they are not. So there are, because of this previous example, some configurations are more likely and some configurations are less likely. So this is the similar exercise for 3 by 3 square lattice. Here also, I see that they are uniform probability for BTW, but non-uniform probability in non-abelian BTW, and their numbers are like this: 1, 0, 3, 5, 2 in the recurrent states, and this is the transient states, etc. And this non. I could not do 4 because these 4 will need 16, 4 to the power 16 number of memory locations, and I do not have access to that much RAM. Just 1 second. Okay, so forbidden subconfiguration, the general definition of the forbidden subconfiguration is this, that you consider a cluster of sites in the stable configuration, and if on this cluster of sites, if this happens that the HI of the number of sand grains, HI or the height of the pile sand column at that site, or the number of sand grains at each and every site is less than the coordination number ZI of I within the cluster, then this is called a forbidden subconfiguration. So that is the generalized definition of the FSC, and the claim is that in the stable state you cannot get a FSC at all. So in the transient state, or that means those states which appear in the stationary states, there are only states which are without FSC, and they are called transient states, and they are called recurrent states. And these recurrent states, they occur with equal probability in the stationary state. So if you consider this, this is the whole entire phase space. So transient state, you start from any arbitrary randomly selected height configuration. This is most likely to be in the transient state, and you follow the dynamics, and you will ultimately land up in the recurrent states zone of recurrent states, and you will be visiting different sites in the recurrent state with uniform probability. So that is the dynamics of this, irrespective of where you start with. You can start from here, you can there, or etc. etc. Your final this state is here, and this volume of this is of zero measure. That is the total volume compared to this. This has a zero measure. So the so now what is the guarantee that L by L lattice, we went up to 3, but L by L lattice, general lattice, that also can be is also not having any forbidden subconfiguration. So that needs to do a bonding process. The lattice one needs to go through a lattice, the lattice through a bonding process, and this prescription of the bonding process has been advised by, has been described by Satya, Majumdar, and Deepak in their paper. And this goes like this: that if you have a cluster of sites, and then you check that some sites are not obeying the rule that their heights are less than their local coordination number. If it is so, you just kill them. Okay, just eliminate them. Then you get a rest of the a shorter, smaller subconfiguration, and you again ask the same question, that if some number of sites are violating this condition, hi greater than equal to zi, then you kill them. So you recursively kill those sites which are not obeying the forbidden subconfiguration rule. And then ultimately, if you come up with a left with a site set of sites which everywhere this for FSC rule is obeyed, so that is a FSC. If the lattice is having at least one FSC of any size, then this is not a recurrent configuration, this is a transient configuration. So this is the burning process, and this is has been done in this way. The configuration, the height configuration are obtained by running NABTW restricted height Sandpile. And these pictures, you see that here what is being varied, then n. What is n? N is the n times L square is the number of particles you dropped. And then this has led to average height, this one. And the number of sites you burnt is 18%. So 18% sites can be burnt here. Here the fire, initially the fire is outside the boundary. You can imagine that there is a shadow layer outside the boundary, and every site on the boundary is actually burning. So the fire will propagate inside, towards inside the lattice. And here it is 18%. You increase the number of particles dropped is 2.1 times L square. So the average height also increased, and the fraction of the burning sites, burnt sites, that also increased, and etc. Here finally you arrive at this where 100% sites are burnt. So when 100% sites are burnt, so that is considered a recurrent state, and that is in the stationary state. It's a recurrent state in the stationary state. So I calculated this the fraction of burning sites. Okay, its variation with n. So n is a monotonically increasing number. Okay, H average is not, because H average will be going to a stationary value, but n will increase monotonically. It's a number of particles you drop, and you get these type of things, and this type of curves for 32, 64, 128, 256, and you can make a scaling like this. And with that scaling, and this is n half, means it is the value of n where this fraction is half. If you subtract that, they pass through very accurately, they pass through the same point, but not exactly. And then you make a scaling, and this you can determine, calculate the value of the in the asymptotic limit, it is 2.03. And there is another thing is this, that when you drop a particle, the amount of the set of sites you burn and the lattice, when you drop the next particle, the set of sites are burned. This delta B, if you consider a delta B, this delta B could be positive and negative. So this is this fluctuation. Okay, and this fluctuation ultimately this becomes 0 when it 100% sites are burnt. So this becomes 0. But then there is a maximum fluctuation. You consider we try to locate when delta B is maximum, either plus or minus, and then taken the value of n corresponding to that value of delta B, where delta B is maximum. So this is this one, this variation. And then another quantity we measured average value of n when 100% sites are burned. At that time, the value of n, average value of n is this one. And then this is both plots are with L to the power minus 0.55 and 0.50. So they are going to constant value when L tends to infinity, but they are these final values, asymptotic values are different, and they are distinctly different. With this they cannot be equal. But then there is another quantity measured, that is the average height when there is the maximum value of delta B. So that also gives another value of asymptotic value of the average height, and this is 2.058. So this 2.058 is compared with 2.057 we measured a few slides before. So they are very consistent. So this is another way to measure the average height of the sandpile in the stable state. So this is a typical multiple zone. How many minutes I have? I started late. Another 5. Oh, okay, good. So so this is a multiple zone picture of multiple toppling, multiply toppled zones. So 1, 2, 3, 4, 5, 6. These are colors. So the those sites which have toppled only once, they are black, and etc. These are twice, thrice, fourth, etc. So you can understand that the sites which are at the boundary, they must topple only once, because they have they cannot have another all the 4 sites to topple, because all the 4 sites, neighboring sites, have not toppled. That's why they toppled only once and not the second time. So here we have given this for 4 comparisons. In BTW, the average height through the lattice, we are considering height profile through a midsection, through a cut, middle cut. So BTW, this is uniform. For any BTW, it is like this. It has a dip. And for F3, F2, F1, these are the fraction of sites with height 3, 2, and 1. So here also it is like this. Okay, compared to BTW, there is it is flat or uniform. So what does this mean? This means that the near the center, the sites are having less probability to be 3, but in an avalanche will be activated only from the site where there is a height 3. So their population is less here, and that means they are more sparse in the central region, and that's why the avalanches in the central region, their also sizes are on the average, they are also small. So that is seen by this 3-dimensional picture. This is the average size of the avalanche originated from a point xy. Okay, so this is the 3-dimensional picture, and S and Y, this is the sandpile, and this is looks like this. And this is again a cut, middle cut of this this profile for the different system sizes: 32, 64, 128, 256, like this, and this goes like this. So so let us now compare the largest avalanche in 2 minutes. So this is the largest avalanche where all sites are 3, and you drop a sand grain right at the center. The avalanche resulted is a Smax, and this Smax for a 11 by 11 lattice, for BTW it looks like this. You see that here all sites have toppled once, then twice, thrice, etc. And this is the avalanche size is given by this formula, and that means the avalanche size goes as L to the power 3. But for any BTW, this is for any BTW, this is like compared to 286, this is a 739. Why? Because this is these sites on the boundary, they can topple 4 times. Because here they do not need 4 particles to come back for a second toppling, and that's why the boundary sites can topple more than once. And here the center site has toppled 11 times compared to 6 times here. So here this is the size is more, and this is the final stable configuration for this. So now the average size for BTW, which is L to the power 298, asymptotically L to the power 3, has this, the slope has variation with L. Here compared to 3, it is 3.90. So it varies between 2.8, 3.86 and 3.96. So it is tending towards 4. Similarly, Tmax, this is tending towards 2. So these are different from this. This behavior is different from between the 2 models. And there is a drop number distribution for NABTW. So somebody was asking for BTW, we measured 30 years before. It was having a exponential decaying form. But for NABTW, it is a power law. And power law with this distribution, I don't think it. I'll be surprised that if it is one, and one needs to. If one can find it analytically, then this could be verified. And so this is again one interesting to check that for HC equal to 4, whatever I said is for HC equal to 4, and this is the avalanche profile. But for HC equal to 5, this will be like this. For 6, 7, 8, and for BTW, it is like this, which is just a parabolic form. So the most non-trivial variation of this restricted height model is for when it is HC equal to 4. And next is avalanche size distribution for BTW. So that is the main question. Many people have given numbers for this tau, avalanche size exponent tau. Deepak and Satya in their paper said it is 8 by 7, so 1.14, etc. And we said 1.20, but there are other numbers, etc. So this is not a settled number yet, but people do believe that this is. Some people also said that this could be a multifractal distribution, but that's another story. For single distribution, the exponent is not agreed upon by many different authors. For NABTW, this is much better. The collapse is much better, and I think there would not be much controversy here. And this is getting 1.28. So 1.28 is a number which is actually gives you idea that it may be similar to the stochastic Sandpile model. And okay, before that, let me show that this BTW or NABTW, there could be a difference in the sense that this is the largest lattice size that I have studied, and in BTW, their numbers goes as this is the slope value in a box in this region, the maximum state region, and their number goes as 1.11, 1.3 like this. NABTW, it is much higher than these numbers, and they are different. And you can see that this has a larger slope compared to this here. And so what happens to the stochastic models? In stochastic model also one can define that height restricted Sandpile model. Actually, the Dickman et al. Proposed this model here only, but for a closed system. They were interested in this adsorbed to active phase transition, but not in avalanche dynamics. But if one does this avalanche dynamics here, then one gets this 1.27 very accurately. So it may happen that the NABTW avalanche exponent is the same as this stochastic Sandpile model exponent. And finally, the drop distribution is also having the same power law here. So summary is this, that it's a BTW model, modification of that, and there is a non-uniform heights probabilities in the stationary state that may make some difference in their behavior. And these are the references, and this is the picture. I have snapped 12 years before, and that is my best picture. So this is where I live here in Calcutta.
Thank you, Subhrangshu. Are there any questions? Yes.
Yeah, so I have a question regarding the burning of the states that you mentioned. So when you add the grains to each of the sites, initially you will have your transient states, right? And when you reach a so when you reach a recurrent state in some local region of that, at that time you will stop adding the grains by the law of the Sandpile, right? And you will let the boundary of that recurrent state do the sandpile, obey the sandpile law, and then will still be adding grains in the other regions of the sandpile? How, I mean, exactly does it work? I didn't clearly get it. Yeah, how does the burning?
Two things.
Okay.
First, the dynamics of the VTW model is clear to you, and any VTW model is also clear to you. So for this burning process, we are following exactly the same dynamics. This is number one. Number two, the whole job is to check that when is the first time there is a burning, complete burning of the lattice. Okay. So what I am trying to say that if you drop 2.05 times L square number of sand grains, then the configuration will not burn. The fire will stop here, and you will see that no more sites are burnable. Okay, for the next time step. So the fire will stop here, and their fraction is 18%. So you drop more, that means you are approaching more to the critical point, stationary state, and then it is a 44%, and then even more 91%, and at this density, at this number 2.153, you get 100% burning for the first time.
There was another relation involving K and S that I didn't understand. I think in the previous slides, 1 or 2 slides. What was that speaking to?
I'm going back.
Yeah, this one.
Oh, so this is nothing but it's a binary number, but it's not a binary number where instead of binary states, it's a 4 states. So I am constructing a number depending on the states of the 4 states of the 2 by 2. Okay, so there are 4 to the power 4 states, 256 states. So 2, if it is 0, 1, 2, or 3, so this is the number that I multiplied by 4 to the power 3. The second one, 2, 1, this I multiplied by 4 square, and etc. These are the heights. This A, sorry, I should have written, that is true. I should have written H rather than S. So typically I use for my computer code S as the height variable. So that is a mistake.
So Manna, you had a picture with mean S as a function of the 3D plot. Can you?
Height, that is the S, yes. I don't know where it is. Yeah. Yeah.
So there are these 4 bumps. Is it clear why they occur?
These bumps, I have also seen. First of all, this is the average plot. Again, no, I don't have a very good reason for that. I have observed that this is happening, but again, it's a boundary effect, and also I thought there could be something non-trivial here also, like this 3 or 4 points are there, whether they are symmetrical distribution or not. I should take a contour plot for that, then that will be more clear, these things.
Okay, so for the sake of time, let's close the session.